Hi, welcome back to the lecture series on analog electronics. This lecture series is a part of Let's Crack the Gate initiative by TEQIP Faculties. So far, we have been discussing transistor models, how we can use these transistor models for small signal analysis. Today, we'll do some more analysis using these models we know. After that, we can go for the high frequency small signal analysis of these amplifiers. In the previous lectures, we have seen this low frequency small signal analysis of these amplifiers. So today we'll try something new. Okay, let's begin. So far we have discussed common emitter amplifiers and common collector amplifier, which was called emitter follower circuit, right? So what is left? Common base amplifier. So today we will analyze this common base amplifier, that is the small signal low frequency analysis of this common base amplifier using the models we know. So let's see how this common base amplifier looks like. So there is our transistor with its emitter, base and collector. We are applying fixed bias here. So there is our RC. Here we have VCC. Here we have RB. Now here we have a coupling capacitor, and now this is connected to the ground. This is RB, this is RC. Now there is an emitter resistor here, which is called RE. We will be giving the input here because this is common base. Base is common to both input and output, and base is close to the ground. Now here we have our signal with its RS and supply. PS, RS, and output will be taken from here. Here we have our V in. So this is the circuit of a common base amplifier. Now this capacitor is called base capacitor CB. Here we need one more capacitor, a coupling capacitor CC. Here also there is CC, coupling capacitor. So you know how to do DC analysis. We have already done DC analysis for these type of circuits. So we need DC analysis to find the operating points, and after that we'll do the AC analysis. Now you know that for low frequency and mid-band frequency, these capacitors will have a reactance which is equal to 0 or nearly 0. So they can be considered as short circuits, and DC supplies has to be removed. So this RB is, this end is connected to ground, and this end is connected to ground. So RB is basically, RB is basically not in the circuit, right? Because base is now directly connected to the ground through this. So now we can draw the AC equivalent diagram. That will look like this. Transistor, base is now connected to ground. Then at the collector, this RC is now connected to the ground, and this capacitor is short circuited. RL is connected to the ground. So here we have RC and a parallel RL like this. Here plus or minus V out. This is RL, this is RC. Now if we look at emitter, there is our emitter resistor, RE, and here we have RS and our signal Vs. Across this we have our V in, and this is R. Let's redraw this again. Now this can be redrawn into a circuit that looks like this. At the emitter we have Rs, Re. Here we have Vs. Base is connected to ground. At the collector there is Rc and Rl. Here we have our output. Now for this we will be using RE model. So here we have our base. Base is connected to the ground. Here we have emitter. Between emitter and base we have our RE. If you remember, this model is also called T model. Now we can see a T here. Now there is a current controlled current source, and the source is alpha IE. Here we have base current IB and emitter current IE. This collector is connected to RC, is parallel with RL. Here there is the output. Now at the input side, here we have RE, RS and Vs. Now this is the equivalent circuit of our common base amplifier. We also know that across our RE we have plus or minus V in. Okay, so the circuit is complete. We can start the analysis. Before that, we will identify the resistances. This is Rn. This is Rn dash, which is the same as Zin, and here we have Z out. Write it, Zin, and here we have Z out dash or R out dash. Okay, so the first parameter is input impedance. Zi, you know that Zi equal to Vi divided by Ii. So what is Vi? Vi is the voltage drop across Re. So that can be written as, so in order to find out Zi, we will first find out Rn. Rn is the resistance when we are looking at this from here. So that will be equal to Vi divided by IE, and we can see that here we have Vi, there is no voltage drop here. That means across this point also we have Vi. So across Re we have Vi. That means Vi divided by IE will be equal to Re. Now this is very small because we know that Re at room temperature is equal to 25 ohms. So Rn is very small. And if we consider Zi is nothing but Re parallel small re. Since Re is small, Zi is also very small. Okay. Next thing is output impedance. We know that our input current is IE. So output impedance is V out divided by I out if input equal to 0. If there is no input, there is no IE. If I is equal to 0, alpha I is equal to 0, that means across this we will have an open circuit. So if this is open circuit, when we look from here, we can see that there are two resistors here, RC and RL, and they are in parallel. So Z out will be equal to RC parallel RL, and if RL equal to infinity, that is if the output is open, in that case Z out will be equal to RC. So this is Z out, this is ZI. Next parameter is voltage gain. AV. AV is equal to V out divided by VI. Look at the circuit diagram. This is VI. We can see that VI is equal to minus IE/RE, right? VI is the drop across RE and the direction is like this. So VI is equal to minus IE into small RE, right? Now what will be V out? We know that this can be written as RC parallel RL, and the output current will be like this, which is I out. So output voltage will be equal to I out into RC parallel RL. We know that I out is nothing but minus alpha into IE. So V out can be written as minus alpha IE into RC parallel RL. Now AV is given by minus alpha IE into RC parallel RL divided by minus IE RE. IE and IE cancels, minus and minus cancels. So what we get is alpha into RC parallel RL divided by RE. So this is the voltage gain. If again we can approximate RL to infinity if the output is open, we get AV as alpha into RC divided by RE, and we know that alpha is approximately equal to 1. So that gives AV as RC divided by RE. Now the last parameter is the current gain. AI is equal to I out divided by II. Now we know that I out is nothing but minus alpha IE minus alpha IE, and II can be approximated to IE because this is a low resistance, so most of the current will be flowing here only. So II is equal to minus IE. So we get AI as alpha, and we know that alpha is approximately equal to 1. So AI is approximately equal to 1. So this is the current gain of common base amplifier. So here we have all the important parameters: input impedance, output impedance, voltage gain, and current gain. I think now we have done enough small signal low frequency analysis. So we can go for the small signal high frequency analysis. Okay, but there is one thing left, that is in the small signal low frequency analysis we have to discuss H parameter. So that part is left. But in the high frequency analysis we use RPi and RE model. So I am continuing with RPi and RE model. After finishing high frequency analysis, we will come back to the low frequency analysis by H parameter model. Okay. So before getting into small signal high frequency analysis, we need to learn a few more things, and those things are Miller's theorem, After that, we need to learn about junction capacitance. Before getting into the junction capacitance of BJTs, we need to know what is junction capacitance by looking at the junction of a diode. Okay, now we'll start with Miller's theorem, and after that we'll go for the junction capacitance. If there is an impedance that connects the amplifier's input and output ports, it will add a great deal of complexity in the analysis process. So Miller's theorem gives us a solution for that. And let's say we have a two-port network. That could be our transistor model. So this is our two-port network. Here we have plus or minus V1. Here we have plus or minus V2. And there is an impedance that connects this input and output terminals. Let's say this is of the value Z. Now this is a linear two-port network. We know that for our operating frequencies and operating points, we can consider our transistors to be linear circuits. Now this is I1, this is I2. Now Miller's theorem says that this circuit can be replaced by an equivalent circuit, and that equivalent circuit will look like this: a two-port network, and the impedance that was connecting input and output terminals can be split into two. Now this is Z1 and this is Z2. This is again our linear two-port network. Actually, I1 is not this and I2 is not this. This is I1 and this is I2. Okay. Now here we have plus or minus V1. Here we have plus or minus V2. Through Z1, here I1 flows and here I2 flows. And here there is a relationship between V1 and V2, and that relationship is V2 is equal to AV1, where A is the gain, right? Now we can derive the equations for Z1 and Z2 in terms of Z and A. In this case, on the left hand side, we can write Z is equal to V1 minus V2 divided by I1, and that is same as V2 minus V1 divided by I2. Also, I1 can be written as V1 minus V2 divided by Z. Similar way, I2 can be written as V2 minus V1 divided by Z. In this case, on the right hand side, Z1 can be written as V1 by I1, and that will be equal to, we know I1, which is V1 minus V2 divided by Z. So Z1 will be V1 divided by V1 minus V2 divided by Z, which goes up. So V1 into Z divided by V1 minus V2. We can divide the denominator and numerator by V1. So that will give us Z divided by 1 minus V2 by V1. And we know what V2 by V1 is, which is equal to A. So Z1 is equal to Z divided by 1 minus A. Now Z2 can be written as V2 by I2, which is equal to V2 divided by I2 is V2 minus V1 divided by Z. So Z goes up. We need to divide both the numerator and denominator by V1. that will give us A into Z divided by A minus 1. So Z2 equal to AZ divided by A minus 1. I am rewriting it here. Z1 is equal to Z divided by 1 minus A, and Z2 is equal to AZ divided by A minus 1. By using these equations, we can find out the value of Z1 and Z2. Now we can see that Z1 is only connected to the input terminals and Z2 is only connected to the output terminals. There is no common impedance between input and output. So this will make our analysis easier. When I am explaining the next session, you will understand why this will make our analysis easier. Now our next topic is diode junction capacitance. I already told you that. We'll first see what is diode junction capacitance. After that, we'll go for the BJT junction capacitance. Okay. Now we know that a capacitor stores electric charge in the form of electric field. So normally in a capacitor there will be two parallel plates of conducting materials, and they will be separated by a non-conducting material, a dielectric material, right? So in a diode, where is this plates and where is this charge separation? So we know that is if we have a diode like this, we know that there is a junction here between the p type and n type material. I am drawing an exaggerated junction just for understanding. So this is the junction, this is our p type material, this is our n type material, here we have our leads, right? This is the junction. What is there in the junction? There is the depletion layer, and we know that depletion layer has ions. Those are charged atoms. So here on the p side it will be negatively charged ions, and on the n side it will be positively charged ions. There are no majority charge carriers, or there are no carriers in this depletion layer. That means the resistance of this depletion layer is very high compared to these p and n type materials. So at the p we will have holes, n we will have electrons. Now there are charge carriers in p and n region. That means the resistance of these two will be low. So they can be considered as our metal plates or the leads of the capacitor, and these junctions can be, that is, the p type and n type regions will act like the electrodes or conducting plates of the capacitor, and the depletion region of the p-n junction diode, it has a high resistance. So depletion region will act like a dielectric. So there is a charge separation. There are regions that act like electrodes, that is the conducting plates. So that means this region will look like a capacitor. There is also this point that in the depletion region, electric charges do not move from one place to another. That means they will be producing an electric field there, right? So here charge is stored at the depletion region in the form of an electric field. So we can say that at the depletion region we have a capacitor, right? So what I have drawn here is a large depletion region. That means this diode is reverse biased, right? In the reversed biased diode junction, there is a capacitance called transition capacitance. And this capacitance is given by Ct equal to epsilon A divided by W, where A is the area of the junction and W is the width of the junction. Now this W, which is the width of this transition region, is a function of the applied reverse voltage. So Ct is a function of the applied reverse voltage. So it can also be written as Ct is equal to Cj0 divided by 1 plus V reverse bias divided by Vo all raised to M, where M is equal to half for abrupt junction and 1/3 otherwise. So Ct can be represented by these two equations. This is the direct relationship between Ct and reverse bias voltage. Now we know that a transistor can be forward biased also. So in the forward biased transistor, the width of the junction is very less. So let's say this is our transistor. This is the new width due to forward bias. Again, there is a capacitance here. The depletion region has not completely vanished. That means there will be transition capacitance. But in this case, there is some other capacitance called diffusion capacitance, which will be more than the transition capacitance. And the diffusion capacitance CD, and this occurs in forward bias. This is given by tau f into Gm, where tau f is the forward transition time and we already know what Gm is. Gm is the transconductance ratio. So if we draw the equivalent circuit of a diode now, it will look like this. This is our diode, and there will be a capacitance between the input and output, that is between the anode and cathode terminals of this diode. If the diode is reverse biased, this is equal to Ct, and if the diode is forward biased, this is equal to Cd. So this is the equivalent circuit of a diode if we are considering the capacitance, that is the junction capacitance. Now we can see what the junction capacitance of a BJT look like. So in a BJT, there is one more junction. There is our base, emitter and collector. Let's say this is emitter, this is base, this is collector. So this junction for amplifier will be forward biased, right? Emitter base junction will be forward biased. So at the emitter base junction, we will have the diffusion capacitance. The collector base junction for this will be reverse biased. So at the collector base junction, we have the transition capacitance. This is a PNP transistor. This CD is also called C pi, and the Ct is also called C mu. And we already know the equations for Ct and Cd. So the equations for diode, diffusion capacitance and transition capacitance hold for this BJT also. Okay. So the next thing is we can do the small signal high frequency analysis of a BJT. And you might be wondering why we were not considering this at the low frequencies. So CD and CT are very less. At low frequencies, the reactance offered by CD and CT. Let me represent that by XCJ. J means junction, so this means junction capacitance. It can be CD or it can be CT. This is equal to 1 by 2 pi F Cj. Now F is low, Cj is also low. So these reactances will be very high value and we can take them as infinity. That means at low frequencies these capacitance will act as an open circuit. So we don't have to consider them when we are analyzing our BJT using small signal low frequency analysis. Now when we talk about small signal high frequency analysis, at high frequencies this XCJ will have values, that is finite values. So we have to consider XCJ, that is the junction capacitance, as well in the analysis. Now we can do the small signal model for high frequency. We have the pi model. The pi model looks like this. Here we have R pi. Here we have the current source, that is voltage controlled current source, and this was our model. Now this is R pi, this is base, emitter and collector, and this is GM VBE. Now this is high frequency model, so we have to consider the capacitance also. So between base and emitter we have a capacitance. We can call it CD or C pi. So there is our C pi. And between base and collector we have another capacitance, because this is the reverse biased junction. So this is CT or C mu. Now this is the model of our BJT during high frequency analysis. Okay, here we have our IB and IE. This is IC. None of these things change. We can also draw this as a current controlled current source type of pi model. So here we will have a current controlled current source. I am not considering RO here because RO is very high, so it can be considered as an open circuit. This is R pi, C pi, emitter, base, collector. This is beta IB, this is IB, this is IE, and there is one more capacitance between base and collector, and this is C mu. So this is the model. This is the high frequency model. We can use either the one on the left or the one on the right. Now we can do the analysis of one of the circuits we have already done, and after that you will be able to do the analysis by yourself. Okay, let's go. We'll do the common emitter short circuit current gain. In this case, we are assuming that there is a bypass capacitor at the emitter. So RE will not be present in the circuit. RE means capital RE will not be present in the circuit. And this is a short circuit current gain. That means the output is shorted. That is RL equal to 0. Now we can draw the circuit. Here is our Vs. I am directly going into the equivalent circuit model. There is the Rs, and here we will have RB, either just RB, a single resistance, or the combination of R1 and R2, which is R1 parallel R2. So this is RB. Here we will have our model. Here we will have RC, and emitter is grounded, and here also there is a short circuit because RL is equal to 0. This is RC. This is C mu, this is C pi, this is R pi, and this is GM VBE. Now this is our input circuit. Now there is a capacitance connected between the input and output terminals. This is C mu. Now here we can apply Miller's theorem. So we know that there is an impedance between input and output terminals, which is Z. So Z1 will be given by, that is the input terminal impedance will be given by Z divided by 1 minus A, where A is the voltage gain. So let's represent it by AV, and Z2 is equal to AV into Z divided by AV minus 1. If Z is a capacitive reactance, then Z is given by 1 by j omega C. Then Z1 will be given by 1 by j omega C1, and Z2 will be given by 1 by j omega C2. If you apply this in this equation, that is Z1 equal to Z by 1 minus AV, we will get C1 is equal to 1 minus AV into C, and C2 is equal to AV minus 1 into C divided by AV. So in this case, if we apply this Miller's theorem, we will get two capacitance, one here, let's call it C in, and one here, let's call it C out. Now C out is across a short circuit, so we don't have to consider that. We can find out C in. C in will be equal to C into, that is C mu into 1 minus AV. Now if you look at the figure, this is V out, the voltage across this. So V out is equal to 0. That means AV, which is equal to V out divided by Vi, will be equal to 0. That means C in will be equal to C mu. Now we can redraw this figure. So there is our Vs, Rs, Rb, then comes our R pi, and this C mu is converted to C in and C out. C in is now C mu. So this C mu is connected across this C pi. So the parallel combination of C mu and C pi will be across this terminal. So here we have C pi plus C mu, and on this side there is only GM VBE and this short circuit. This is the output side. Now our input voltage is here, which is Vi. This is nothing but the voltage between base and emitter, which is VBE. So Vi is equal to VBE, and now we can write the value of current gain. This was our aim, to find out the short circuit current gain of common emitter amplifier. So current gain AI is equal to I out divided by II. Here I out is IL, here I out is IL, and II is the current here. Now IL is equal to, when you look at the figure, we can see that it is minus GM VBE, and II can be written as, there are three parallel reactances, one RB, RPi and C pi plus C mu. Let's say the combined admittance is Y in, so II is equal to VBE into Y in. Now we can write AI is equal to minus GM VBE divided by VBE into Y in, that is equal to minus GM divided by Y in. Y in is equal to 1 by RB plus 1 by R pi plus j omega into C pi plus C mu. So we can write AI as minus GM divided by 1 by RB plus 1 by R pi plus j omega into C mu plus C pi. So this will be the value of AI. We can make an assumption here. Normally the value of RB will be very much greater than R pi. So 1 by RB can be equated to 0. So now AI will be equal to minus GM divided by 1 by R pi plus j omega into C pi plus C mu. Now R pi can be multiplied here, so this becomes minus GM into R pi divided by 1 plus j omega C pi plus C mu into R pi. Now this GM into R pi becomes beta, so this is minus beta divided by 1 plus j omega divided by omega h, where omega h is equal to 1 by R pi into C pi plus C mu. Now this AI equal to minus beta divided by 1 plus j omega divided by omega h, this is the equation of a low pass filter, okay, where its cutoff frequency is omega h equal to 1 by R pi into C pi plus C mu, or in frequency terms it can be said as Fh is equal to 1 by 2 pi into R pi into C pi plus C mu. This is the cutoff frequency. So the gain versus frequency graph of this will look like this. This is modulus of AI. This is F, frequency. It will look like this. Okay. Now if you take the modulus of AI will be equal to beta divided by root of 1 plus omega square by omega h square. This beta by root of 1 plus omega by omega h whole square. It can also be written as beta divided by root of 1 plus f by fh whole square. When f is equal to 0, the value is beta, the magnitude is beta. And when f and fh are the same, that is when frequency becomes equal to fh, the magnitude becomes equal to beta by root 2. That is, there is a 3 decibel decrease in the magnitude. So this cutoff frequency is fh. Now we have done one analysis using this high frequency small signal model of a transistor. This is not that normally asked in GATE, so we may not be doing more problems related to this. So I am winding up here. We have done the small signal low frequency analysis using RPi and RE model. We have done the small signal model for high frequency using RPi model. Now what is left is using the H parameter model for low frequency small signal analysis. We'll do that from the next class onwards, and until then,